Domain namespace and resource records, namespace specifications and terminology. The domain namespace is a tree structure. Each node and leaf on the tree corresponds to a resource set which may be empty. The domain system makes no distinction between the uses of the interior nodes and leaves. Is this a typo? So they make no distinction between the uses of the interior nodes and leaves, and this memo uses the term node to refer to both. Each node has a label which is 0 to 63 octets in length. Brother nodes may not have the same label, although the same label can be used for nodes which are not brothers. One label is reserved, and that is the null, i.e. 0 length label used for the root. The domain name of a node is the list of the labels on the path from the node to the root of the tree. By convention, the labels that compose a domain name are printed or read left to right, from the most specific, lowest, furthest from the root, to the least specific, which is highest, closest to the root. Reminds me of Big versus Little Indian. Internally, programs that manipulate domain names should represent them as sequences of labels, where each label is a length octet followed by an octet string, because all domain names end at the root, which has a null string for a label. These internal representations can use a length byte of 0 to terminate a domain name. By convention, domain names can be stored with arbitrary case, but domain name comparisons for all present domain functions are done in a case-insensitive manner. Assuming an ASCII character set in a high order 0-bit, this means that you are free to create a node with a label A or a node with a label lowercase a, but not both as brothers. You could refer to either using A or A when you receive a domain name. When you receive a domain name or label, you should preserve its case. The rationale for this choice is that you may someday need to add full binary domain names for new services. Existing services would not be changed. When a user needs to type a domain name, the length of each label is omitted and the labels are separated by dots. Since a complete domain name ends with the root label, this leads to a printed form which ends in a dot. We use the property to distinguish between a character string, which represents a complete domain name, often called absolute. So, for example, not sure how to pronounce that, but then you have dot, capital ISI, capital EDU. So we could distinguish between that, or a character string that represents the starting labels of a domain name, which is incomplete and should be completed by local software using knowledge of the local domain, often called relative. So, for example, that word used in isi.edu domain. Relative names are either taken relative to a well-known origin or to a list of domains used as a search list. Relative names appear mostly at the user interface, where their interpretation varies from implementation to implementation, and in master files, where they are relative to a single origin domain name. The most common interpretation uses the root dot as either the single origin or as one of the members of the search list. So to a multi-label relative name is often one where the trailing dot has been omitted to save typing. To simplify implementations, the total number of octets that represent a domain name, i.e. the sum of all label octets and label lengths, is limited to 255. A domain is identified by a domain name and consists of the part of the domain name space that is at or below the domain name, which specifies the domain. A domain is a subdomain of another domain if it is contained within that domain. Oh my god, I just deeply regret reading that. How worthless. So this relationship can be tested by seeing the subdomain's name ends with the containing domain's name. So for example, ABCD is a subdomain of B, CD, CD, D, and then nothing. So all of this is sub to all of that, which is also then sub to those two, and then that, etc. Alright, so here we are at Administrative Guidelines on Use. As a matter of policy, the DNS technical specifications do not mandate a particular tree structure or rules for selecting labels. Its goal is to be as general as possible so that it can be used to build arbitrary applications. In particular, the system was designed so that the namespace did not have to be organized along the lines of network boundaries, name servers, etc. The rationale for this is not that the namespace should have no implied semantics, but rather that the choice of implied semantics should be left open to be used for the problem at hand, and that different parts of the tree can have different implied semantics. For example, the adder ARPA domain is organized and distributed by network and host addresses or address because its role is to translate from network or host numbers to names. NetBIOS domains, so see those RFCs, are flat because that is appropriate for that application. So there's more of like a bookmark than anything. However, there are some guidelines that apply to the normal parts of the namespace used for hosts, mailboxes, etc. that will make the namespace more uniform, provide for growth, and minimize problems as software is converted from the older host table. The political decisions about the top levels of the tree originated in RFC 920. Current policy for the top levels is discussed in 1032. Mailnet conversion issues are covered in RFC 1031. So what is Mailnet? Here's the Wikipedia on that. It's a military network. That's all I'll say about that. Now, lower domains, which eventually are broken into multiple zones, should provide branching at the top of the domain so that the eventual decomposition can be done without renaming. Node labels, which use special characters, leading digits, etc., are likely to break older software, which depends on more restrictive choices. Okay, so here we have some technical guidelines on use. Before DNS can be used to hold naming information for some kind of object, two needs must be met. A convention for mapping between object names and domain names. This describes how information about an object is accessed. And then RR types and data formats for describing the object. These rules can be quite simple or fairly complex. Very often the designer must take into account existing formats and plan for upward compatibility for existing usage. Multiple mappings or levels of mapping may be required. For hosts, the mapping depends on the existing syntax for host names, which is a subset of the usual text representation for domain names, together with our R formats for describing host addresses, etc. Because we need a reliable inverse mapping from address to host name, a special mapping for addresses into the adder ARPA domain is also identified. For mailboxes, the mapping is slightly more complex. The usual mail address, so you have local part and then the mail domain, is mapped into a domain name by converting the local part into a single label, regardless, and they misspelled it, regardless of dots it contains. Converting mail domain into a domain name using the usual text format for domain names, so dots denote label breaks, and concatenating the two to form a single domain name, thus the mailbox. So here they have this example. It is represented as a domain name by this. So see the dot right there. An appreciation for the reasons behind this design also take into account the scheme for mail exchanges. The typical user is not concerned with defining these rules, but should understand that they usually are the result of numerous compromises. These are compromises between desires for upward compatibility with old usage, interactions between different object definitions, and the inevitable urge to add new features when defining the rules. The way the DNS is used to support some object is often more crucial than the restrictions inherent in the DNS. And that sentence would have best been read by reading out the acronym. So the way the DNS system is used to support some object is more crucial than the restrictions inherent in the system. So here's an example namespace. The following figure shows a part of the current domain namespace and is used in many examples in this RFC. Note that the tree is very small subset of the actual namespace. So there's root, you have mail, edu, ARPA, and then things get broken out that way. I doubt my copy paste transferred correctly or nicely over here. But you get the example. The root domain has 3 immediate subdomains, mail, edu, and ARPA. The ls.mit.edu domain has 1 immediate subdomain named xx. All of the leaves are also domains. Okay, so now we're on 3.5, preferred name syntax. The DNS specification attempt to be as general as possible in the rules for constructing domain names. The idea is that the name of any existing object can be expressed as a domain name with minimal changes. However, when assigning a domain name for an object, the prudent user will select a name which satisfies both the rules of the domain name system and any existing rules for the object, whether these rules are published or implied by existing programs. For example, when naming a mail domain, the user should satisfy both the rules of this memo and those in RFC 822. When creating a new host name, the old rules for host.txt should be followed. This avoids problems when old software is converted to use domain names. The following syntax will result in fewer problems with many applications that use domain names, for example, mail or telnet. So I won't be reading that part to you. They note that while upper and lowercase letters are allowed in domain names, no significance is attached to the case. That is, 2 names with the same spelling but different case are to be treated as if identical. I agree with that decision. The labels must follow the rules for ARPANET host names. They must start with the letter, end with a letter or digit, and have, as interior characters only, letters, digits, and hyphen. There are also some restrictions on the length. Labels must be 63 characters or less. So for example, the following strings identify hosts in the internet. Here's your example. 3.6. Now we're going into resource records. So a domain name identifies a node, and each node has a set of resources. They may be empty, but they exist. The set of resource information associated with a particular name is composed of separate resource records. The order of RRs in a set is not significant and need not be preserved by name servers, resolvers, or other parts of the DNS. When we talk about a specific RR, we assume it has the following: an owner, so this is the domain name where the RR is found, has a type, which is an encoded 16-bit value that specifies the type of the resource in this resource record. Types refer to abstract resources. And then this memo uses the following types. So you have a host address. CNAME identifies the canonical name of an alias. So C for canonical, I assume. HINFO identifies the CPU and OS used by the host. MX identifies a mail exchange for the domain. NS is the authoritative name server for that domain. PTR is a pointer to another part of the domain namespace. SOA identifies the start of a zone of authority. Class, which is an encoded 16-bit value, which identifies a protocol family or instance of a protocol. And this memo uses the following 2 classes: IN, the internet system, or CH, the chaos system. Amazing. TTL is the time to live of the resource record. This field is a 32-bit integer in units of seconds. And AN is primarily used, so just a typo. AND is primarily used by resolvers when they cache RRs. The time to live describes how long a resource record can be cached before it can be discarded. Now we have R data. This is the type and sometimes class-dependent data which describes the resource. A for the N class, a 32-bit IP address. For the CH class, a domain name followed by a 16-bit octal chaos address. What a cool term. CNAME is a domain name. MX is a 16-bit preference value. Lower is better. Followed by a host name willing to act as a mail exchange for the owner domain. And then we have NS, a host name, PTR, a domain name, and SOA, several fields. The owner name is often implicit rather than forming an integral part of the resource record. For example, many name servers internally form tree or hash structures for the namespace and chain resource records off nodes. The remaining resource record parts are the fixed header, so type, class, time to live, which is consistent for all resource records, and a variable part, our data, that fits the needs of the resource being described. The meaning of the time to live field is a time limit on how long a resource record can be kept in a cache. This limit does not apply to authoritative data in zones. It is also timed out, but by the refreshing policies for the zone. The time to live is assigned by the administrator of the zone where the data originates. While short time to lives can be used to minimize caching, and a zero time to live prohibits caching, the realities of internet performance suggest that these times should be on the order of days for the typical host. If a change can be anticipated, the TTL can be reduced prior to the change to minimize inconsistency during the change, and then increased back to its former value following the change. The data in the R data section of resource records is carried as a combination of binary strings and domain names. The domain names are frequently used as pointers to all or to other data in the DNS. That makes sense. So with that, I'm going to stop this video. I'll do a part 3.5 or 3.61 in the future. So stay tuned for that.